Okay, we're math ed researchers, so this comes out of some of our research, so I'll tell you where we did it. We have a graduate course on proof construction, which is designed to improve their proving skills, and that'll be called the proof scores. We also help a real analysis teacher who finds that her students come in and she has to teach real analysis, but they don't know how to prove, so we do a voluntary supplement for her. This will be pretty familiar to you. It's very much more math ed, self-contained notes, etc. They construct their proofs at home, present them in class. They get critiqued, sometimes extensively. That may be not so much more method, but we like to critique them. And we also like to give suggestions on the writing. And we don't give formal lectures, but we do talk about stuff sometimes if they want to know about it. And we're more interested in covering a lot of different kinds of proofs than anything else. And in the supplement, this is a little different because the supplement teacher has one problem a week that she wants to grade and regrade very carefully. So we get it. She gives it to us. We find one that, John usually does this, that resembles it in construction. And we do that one. They come in cold. They don't have to prepare for the supplement. And we do it together. But it's not a template problem. And so we found it's better if they co-construct. So we ask, well, what's the first line? What's the last line? What do you do next, et cetera? And if they get to the last line, they have to unpack the conclusion, change the definitions to fit the theorem, which is not so easy for them, and eventually get to what the mathematicians are interested, where we have to brainstorm. And this is a very slow process if the students are to do that themselves and you really wait for them to do it. And they go up at the board. And we have this theory of situations and actions, and so we see proving largely as an activity, a sequence of actions that can be physical, such as writing or drawing, or mental, such as recalling a definition. And each action is paired with a response to a situation in the partly completed proof. And some situations become linked in an automated way to a tendency to carry out the corresponding action. And we see such automated situation-action pairs as persistent mental structures and have called them behavioral schemas and have written about it. And this is not the problem solving. This is kind of what the students call the setup. So how do we collect our data? Well, we have videos and we have graduate students who take notes. And in between, we look at them and we make observations about what we want to do next, as well as more general observations like I'm going to give today on proving and students' difficulties. So we collected these and we actually categorized them, and we want problems that are above the level of a particular class that have nothing to do with real analysis or with discrete math, but others. And some of these are pretty surprising. And the most surprising for us, maybe they shouldn't after all these years, but were that, this is in the supplement, so they haven't seen this theorem before, it's on the board, they come in and they do things like work on the scratch board. And some people, and this was a student teacher who's going to teach secondary school, cannot copy a definition correctly on the blackboard, okay? Or did not. Maybe he could. But if you miss these important words like for all and the definition of continuity, it's a big problem. And sometimes we have so many students in the supplement that I take one group and John takes another group. 5 works best. And he's prepared 2 theorems. And so at the end, sorry, I'm ahead of myself. All right. Anyhow, I'll say that. I'll continue. They can't talk about it. They can't express things like for all x, or absolute f of x minus f of a is less than epsilon. I mean, I don't know what goes on in their heads if they can't, they write these symbols down and they have no words that go with them. And that's pretty bad. And this one actually came from this here. This is some sophomore student, well, all ages take it, but it's supposed to be a sophomore course. They'll write down suppose x, like they've said something, which is absolutely amazing that they can think they've said something. And our real analysis teacher says the same thing. They say things like suppose x. Well, what do you want to say about x? John always says, suppose car. Okay. And this is the one I meant to, I got out of order about they're unable to articulate the notation that they have just created and used in a proof. And that's pretty bad. Okay. So those were non-mathematical difficulties. These are pretty standard, but we mean more than the usual stuff about using logic to structure proofs, more than contradiction, contrapositive, induction. Okay, so this one is pretty prevalent, especially in analysis. So they somehow don't understand this distinction between using a definition, like you've got a function that's continuous and you want to use that fact, versus proving something about, like, that function is continuous. And it's amazing that they find it so hard. And if you take the sum of continuous functions as continuous, which is one of our proofs, that they find it very hard to know, am I using the definition or am I proving that something satisfies this definition? So we have to work on that because, all right, here's another one in math induction, especially when it's a for all proof, such as all polynomials are continuous, which is another one of our theorems. They have stuff ahead of time, like some product of continuous functions are continuous, but they tend to start with k and go to k plus 1 instead of starting with k plus 1 and going back to k, because if you start with k and you add on a term, you haven't got the most general polynomial of degree k plus 1, and they have to learn that, because I think this is a thing, conjecture, like from high school or other places where they have to show the sum of the first n integers is n times n plus 1 over 2, and they just add the same thing to both sides, and it works there, but it doesn't generally work. Okay, so this one I'm calling metacognitive knowledge and actions, and this stems from sometimes they have what we call detrimental behavior schemas, or they lack positive ones, and Weber called this strategic knowledge, or lack of it. Now this is, I don't know if you find this, but they like to focus on the hypotheses instead of the conclusion. So they take the hypotheses and they run in some direction, and they don't necessarily get where they're going. And it's better if they unpack the conclusion and try and figure out what it would mean to prove that. And here's one that came up that was just kind of interesting. So this was in an analysis supplement, and they were proving something, and they had a set, and they had to pick an element, and somehow they didn't know they could pick an element. They wanted to construct it. But if you know you've got a set and it's non-empty, and if you want an element and there's no special properties, you can just say, here it is, I'm going to give it a name. It's x1, and now I'm going to work with its properties. Okay. Now here's something we call going outside of the proof genre. And let's see what we mean about that. I have trouble with this. I have to hold it. So they have some good ideas, but they don't know how to write it up. Okay, so I think that goes counter to a previous speaker, so I have to talk about our philosophy. We want our students to write proofs like in journals, but at their level, okay, for other students in the class. So some people, and I've had this argument with some professors who want their students to write definitions into proofs, but we do not. If you can find the definition outside the proof, we don't want it inside the proof. And so they'll write the entire definition of continuity in, instead of saying, by continuity of G, we have blah, 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 and continue. And I've just written a paper on the genre of proof, and a certain editor says, put everything in except when it's so obvious, don't put it in. So that's a math editor talking for a math journal for researchers. Okay, you don't write directions such as, I want to show that, or et cetera, unless you have a very long proof that needs that. Okay. Here's something we call conventions of the mathematical register, stuff they just need to know, like the difference between minimum and minimal. Sometimes we have them try to figure that out, but sometimes maybe that's not so easy. Sometimes they can do if and only if proofs because there's an arrow this way and there's an arrow that way. But then one day a girl said, but what's necessary and sufficient mean? So, you know, she didn't catch that stuff. Here's something we call standard techniques of proving, or your toolkit, as the mathematicians say. Okay, you need to know how to show at most one by taking, you know, two names like x1 and x2 and figuring out what properties x1 and x2 have and somehow getting to x1 equal x2. Or you need to know how to prove P or Q by saying, let's assume not P and get to Q, or by assuming not Q and getting to P. These are pretty standard, you know, these notational difficulties. Okay. This happened also in a real analysis class. So they had an N in the proof, and then the kids flip around because they're making the proof on the spot. They flip around through their books or whatever, notes, whatever the teacher's using that we're helping, and they find an N, and they just use it. But the N in the theorem or definition has nothing to do with the N in the proof they're constructing, but somehow it doesn't occur to them. You know, these are all things they need to learn. And of course, the confusion between element of and contained in, and I think we, myself included, make it worse because we use in for everything. And okay, and now this is a pretty typical one. This, we have some topology in our notes, and I'm not going to read all this stuff down here, but it turns out in topology you often have to have an index set or not. And it sometimes is much more cumbersome to have an index set than to write it in some other way. And there's another way down there. And so that's a difficulty to get to know how to use indices. And quantifiers, of course, everybody knows about that. People have trouble. Not understanding the order influences things, not knowing how to interpret it when you have implicit quantifiers, and not knowing the scope of a quantifier. So this is pretty typical. They just have trouble with arbitrary but fixed. I mean, there are students who will do it if you tell them, but they aren't happy. Why? You fixed one. It's only for that one. And it takes, I have another story about that. One of our students who told us and we interviewed took 2 years to get comfortable with that, okay? It's not like you can tell them once and they're happy. They'll do it all right, but they aren't happy necessarily. And now this is what most mathematicians are interested in. We spend a lot of time with what we call the proof framework and stuff like that because students really don't know how to write. But what mathematicians take as for granted, and they want to concentrate on this, you don't get to right away because the students don't know how to write or set things up. So we have what we call types 1, 2, and 3 theorems built into our notes, and this might be an idea some of you would like to think about. Okay, so we have a type 1 theorem, and that's one where the students have to look back for a theorem. The trouble with introduction to proof is there's too many definitions, and they can prove too many things directly from the definition. And so they want to prove everything from the definition, but we want them to learn to look back. So we have some theorems where they should look back rather than going from the definition. So that's our type 1. Then we have type 2, where they have to create a lemma. But it's not a really hard lemma, but it will help. And it will be cognitively more difficult. So we're ratcheting up the things they have to do. And then type 3 is the one that calls for stating a lemma that's not so easy to state and prove. And the one we have is, we also do some algebra and we do semigroups because that's what we used to do in mathematics. A commutative semigroup with no proper ideals is a group. This is not so easy. And we could put in two lemmas, but we don't because we want them to have the experience, if possible, of discovering them. Okay. I had to have some teaching implications. That's what math ed people do, but they're pretty obvious. Okay, you can tell the students about these things. Okay, so maybe you can prevent the worst of them. You can have the students articulate in words the symbols by having them give presentations, which many more math people do. You can encourage them and help them with the connectives, the logical connectives, which are really important. And this bit about using a definition versus showing something satisfying a definition is really important, and I think it needs work. And don't expect miracles, because whatever we do, they have to learn for themselves.